In this video, we're gonna study the final tests, which are ratio tests and root tests. This test kind of easy to, I would say that it's gonna be the thing the easiest to do. However, it's gonna be not quite useful when you have to deal with the previous case that sometimes you're gonna feel that this test is a little bit difficult to determine because you need to compute the limit. Okay, so the thing that we're gonna begin first is called the ratio test. The ratio test, we consider the ratio between an plus 1 and an. Okay, so it's gonna be, we consider the ratio an plus 1 over an, and we're gonna take limit n go to infinity of this guy. We put absolute value for this ratio because we like to have the sequence to be positive kind of. And if you have this limit turn out to be less than 1, okay, less than 1 is going to be conclusion that the series turned out to be absolutely convergent. Okay, so that is your first case. If you have this limit of the ratio turn out to be less than 1, the series turn out to be absolutely convergent. If you have the limit more than 1 or even infinity, it's going to turn out to be divergent. And the important one turn out to be when you have limit equal to 1. When you have limit equal to 1, the situation turn out to be inconclusive. So for this ratio test to work, you need to compute the limit, and the limit gonna be different from 1. If you have less than 1, absolutely convergent. If you have more than 1, it's gonna be divergent. And if you have it equal to 1, it's gonna turn out to be inconclusive. The reason behind this one a little bit, when you have the limit equal to 1, it means that you not be able to distinguish like the term of the sequence. So you not be able to conclude anything about the series. Okay, for example, if you have the sequence negative 1 to the n over n, so for this one, it's going to turn out to be conditionally convergent. And if you compute limit n go to infinity of absolute an plus 1 over an, this guy turned out to be equal to 1. You can try on your own, and you see that this guy turned out to be conditionally convergent. And you see this one also, that this limit n go to infinity of absolute an plus 1 over an turned out to be also equal to 1, and it's turned out to be absolutely convergent. Okay, so we cannot conclude when you have the limit of the ratio turn out to be equal to 1. I will give you two examples. So example 28, we like to determine whether the series is absolutely convergent, conditionally convergent, or divergent. So for this one, you don't have to do something long like the previous case. Okay, so in the previous example, it's going to be kind of long. For this one, you can just apply the ratio test in order to reach the conclusion. So for this one, you have your an. Okay, let me circle our an first. So our an, okay, so our an is this guy. The thing that I would want to teach you first is going to be, can you find an plus 1 for me? Okay, an plus 1 will be, you're gonna plug in n equal to n plus 1. So it's going to be negative 1 to the n plus 1 to the third over 5 to the n plus 1. Okay, so you see like the place that you replace n with n plus 1. I made mistake already. So this guy is going to be n plus 1, sorry. Okay. And so you see that this one will be your an plus 1. And for an, it's going to be negative 1 to the n to the third over 5 to the n. Okay, so this one will be your an. And the thing that you like to find is going to be the ratio between an plus 1 and an. So I'm going to just erase the equal sign, okay? And I'm going to just put the ratio. Okay, so it's going to turn out to be this ratio. And so you see that you need to put absolute value as well. So it's going to be, you're going to put absolute value. Okay, you're going to put absolute value and absolute value like this. Okay, and the thing that you are trying to compute turn out to be, or you like to simplify this guy. Okay, so you see that this one, when you cancel, okay, you can cancel this one and you get -1 left, and you have 5 to the n plus 1 and 5 to the n, so you would have 5 left on top, and you still have the ratio. So in this case, you would get absolute -1. Okay, and you have 5 left. Let me write it with the red color. So it's going to be -1 over 5. Okay, so you see the red color, and you have the green one, which are n plus 1 to the third over n to the third. Okay, so this is how we have absolute value of an plus 1 over an ready to compute the limit. So this one, let me resize this one a little bit. So after we have this one, we're gonna compute the limit. So you see that this one can be simplified further. So when you take absolute value, the thing that will disappear will be negative side. So you would just have 1/3. Okay, so you would just have 1/3. And for your n plus 1 and n to the third turn out to be just, so it's going to be just n plus 1 to the third over n to the third. Okay, so it's going to be just simple like this. And you're going to compute limit n go to infinity of 1/5 n plus 1 to the third over n to the third. And this guy, when you compute, so you're gonna just have 1/5 and you have n plus 1 over n to the third. And so it's gonna be 1/5, 1 plus 1 over n to the third. And you're gonna take n go to infinity. So this one become 0. Okay, so this one becomes 0. So you're gonna have the limit equal to 1/5. Okay, so the limit turned out to be equal to 1/5. And you look at, it's gonna fall into the first case. Okay, so it's gonna fall into the first case, which is smaller than 1. Okay, so this one is your first case. And so the conclusion will be the series turned out to be absolutely convergent. Okay, so is absolutely convergent. Okay, so this is the situation when you have to use the ratio test and you compute the limit of the ratio between an plus 1 over an. Okay, this trick will be used in the following section as well, so I teach you slowly. The next one, okay, like I said, you may have to perform a little bit on algebra for this technique. So you have your an, okay, so you have your an here, and you're gonna first begin with an plus 1. So for an plus 1, you're gonna replace n with n plus 1, and you see that you have two places for n, this guy and this guy. So you're gonna replace them with n plus 1. So be careful on this one a little bit. So it's gonna be 2n plus 1 factorial, and you have n plus 1 factorial square. Okay, so you see that you replace two places here, one place, two places, and you see that this one will be 2n plus 2 factorial over n plus 1 factorial square. Okay, and so you're gonna have to find the ratio. Okay, so you're gonna have an an is gonna be 2n factorial, and you're gonna divide by n factorial square. Okay, so that my an plus 1 and an. We're gonna replace the equal sign, okay, and we're gonna divide, okay, like we did before. So I have this one, and I will have this one, and I will have the longer one. Okay, so this one like this, and I would put absolute value. Okay, so it's gonna be this calculation. Okay, everything look nice. So the algebra that you may have to perform will be, you have to notice that you like to kind of get rid of this guy and this guy, okay? And the thing that you're gonna perform or you're gonna do is gonna be, you're gonna just try to figure out what is 2n plus 2 factorial, okay? What is 2n plus 2 factorial? So you see that 2n plus 2 factorial turn out to be just 2n plus 2, 2n plus 1, okay? And you have 2n up until 1, okay? So that's going to be 2n plus 2 factorial. And you have 2n factorial, it's going to be 2n multiply up until 1 as well, okay? And you have n plus 1 factorial, n plus 1 factorial, let me use different color. N plus 1 factorial here is going to be n plus 1 times n minus 1 up until 1, and you raise square, okay? And for n factorial, you would have n minus 1 up until 1, okay? And you have square. And you see that you can get rid of 2n times until 1, okay? So you can get rid of this guy together with 2n up until 1, okay? So that's gonna be the thing that you be able to get rid of. And you see that you have the common term here with the square. So you're gonna be able to cross this term and cross this term out. So the thing that you will end up or you have left is gonna turn out to be the green term that I highlighted, okay? So it's gonna be just these two green terms that you will have to deal with. So you're gonna compute limit n go to infinity of absolute an plus 1 over an. So this one will be just the green term that you have left up there. So it would be 2n plus 2, 2n plus 1. Okay, so it's gonna be over n plus 1. Okay, so it's gonna turn out to be this one. However, it's gonna be n plus 1 square. Okay, don't forget square here. Okay, so you have square come from these numbers. Okay, so this one will be limit n go to infinity. Okay, and so it's gonna be 4n squared. Okay, so let me multiply this guy out. So it's gonna be 4n squared, and it's gonna be 4 and 2, so it's gonna be 6n plus 2. And on the bottom, it's gonna be just n squared plus 2n plus 1. And you take limit n go to infinity. So this one will become 4. Okay, so this limit turned out to be equal to 4, and it's going to be positive, and it's turned out to be more than 1. Okay, so when you are having the limit more than 1, you are in the second case, so it's going to be diversion. Okay, so it's going to be diversion series n equal to 1 to infinity of 2n factorial over n factorial square is diversion by the ratio test. Okay, so that is gonna be how we use the ratio test. Okay, the next thing that we can use is gonna call another test. It's gonna be the root test. The root test a little bit different from the ratio test, and we're going to use the root test when we have to deal with something like this guy. You see that if you have your an in this form, okay, so if you have your an in this form, this is my an, right? So you see that an plus 1, okay, so this is your an. So you see that your an plus 1 turned out to be very big and messy. N plus 1 to the n plus 1, and it's kind of difficult to use the ratio test. However, it's going to be easier if you be able to just take the n root. If you take the n root of this guy, you see that the power turn out to be cancelled, and you're gonna be able to find the limit quite easy. Okay, so for this one, we're gonna adopt another test, which is called the root test. So in order to use the root test, you're gonna find limit n go to infinity of absolute of an, and you're gonna take the n root. So this one, if you have L less than 1, similar to the previous ratio test, it's gonna turn out to be absolutely conversion. If you have L more than 1, it's gonna turn out to be diversion. And if you have L equal to 1, still you have inconclusive. It can be conversion or it can be divergent. You use other tests. Okay, so when you have inconclusive, it means you use other tests. Okay, so similar to this one, you use other tests. I teach you in the same way. So you see in this case that you have your an. Okay, so you have your an. given by this guy. Okay, so you're gonna put absolute value of an and you raise to the n root. So it's gonna be the n root of absolute value n plus log n over 2n plus 3 to the n. Okay, and this one turned out to be the n root. And so you see that when you have the n root like this, the thing that you'll be able to get rid of is going to be this power n. So the thing that you have left will be without absolute value because everything inside is positive. Okay, so this guy is positive. So absolute with absolute or without absolute is turned out to be doesn't matter. So it's gonna be this 1 over 2n plus 3. Okay, so that will be the n root of absolute an ready for taking the limit. And you're gonna take the limit and go to infinity of n root of absolute an. So it's gonna be limit and go to infinity of the thing that you already computed. So it's gonna be log n over 2n plus 3. And this one turned out to be infinite over infinite that we will apply L'Hopital. Okay, and so you dip on top, you get 1, dip log n, you get 1 over n, and dip 2n plus 3 is going to be 2. And when you take n go to infinity, this turn out to be 0, and the limit is equal to 1/2. It's going to be less than 1. Okay, so the limit is less than 1. So, okay, you gonna have the conclusion. Okay, so this one is gonna be in the first case. So the conclusion turned out to be conversion absolutely. Okay, so the series n equal to 1 to infinity of n plus log n over 2n plus 3 to the n is absolutely conversion. Okay, so this one will be this example. For another one, okay, you have your an, okay, and you see that this guy can be written as -2 over tan n to the n. Okay, so you gonna take absolute value of an and you take the n root. So you get the n root of -2 over tan n to the n. So you have absolute value. Okay. So you see that n and n cancel each other. So you would have absolute value of 2. So it's going to be 2 over absolute value of tan n. Okay, so it's going to be like this. So this one will be this term. Let me change the color a little bit. Okay, so we have the pink guy. And then we're going to compute the limit of the pink guy. So it's going to be limit n go to infinity of the n root of absolute an. So it's going to be limit n go to infinity of absolute, not absolute, 2 over absolute value of arctan n. So it's going to be 2 over arctan infinity. And we don't need to put absolute value because we know that arctan infinity is positive. So it's going to be 2 over pi over 2. So this one is pi over 2, and this will give us 4 over pi. Okay, so you have the limit equal to 4 over pi, and you know that pi is about 3.14. So you have 4 over 3.14 will be more than 1. Okay, so will be larger than 1. So in this case, you're gonna conclude that the series negative 2 to the n, 10 n to the n is divergent. Okay, so that is gonna be how we do this one. The next one, okay, so the next one, you have the series n equal to 1 to infinity of n over n plus 1 to the n square. So for this one, you just identify your an. Okay, so this is my an. The thing that we're gonna compute will be the n root of absolute an. So it's gonna be absolute n over n plus 1. Okay, so it's gonna be absolute n over n plus 1 to the n square. Okay, and you are taking the n root, and you see that it's gonna be n over n plus 1. Okay, and you have n square over n. Okay, so it's going to be n squared over n when you take the n root, and you get rid of this guy is going to be n. So you see that this will become n over n plus 1 to the n. Okay, so that is going to be the n root of an. And for this one, you're gonna compute limit n go to infinity of n over n plus 1 to the n. And this one will be applying the L'Hopital in terms of e. Okay, so this one is gonna be e, and you have limit n go to infinity. Okay, of n, okay, and it's going to be log n over n plus 1, and this one will become e to something, and we're gonna find the yellow limit as usual. Okay, so we're gonna have to find limit n go to infinity of n log n over n plus 1. Okay, I will let you finish this one on your own, okay, to see what is the limit that you will get, and then in conclusion you're gonna get the yellow limit. Okay, and you're gonna conclude whether you have less than 1 or more than 1, and it's gonna turn out to be the conclusion for divergent or absolutely convergent. Okay, so please do this one on your own and use L'Hopital, okay, for sure. The next one, so you see this one, you may think that, hey, how could we deal with something like this? It's not quite nice. However, this one, if you consider an, okay, so this one will be your an. So you're gonna consider absolute value of an. So it's gonna be everything. So it's gonna be 1 over 2 to the n plus negative 1 to the n. Okay, and raised to 1 over n. Okay, so this one turned out to be transforming our n root. Okay, so our n root can be transformed into something like this. And you see that The algebra that we can play is going to be very simple. So it's going to be 1 over 2 n plus negative 1 to the n, everything over n. And this guy will be 1 over 2 to the 1 plus negative 1 to the n over n. Okay, so you have this number. And if you compute limit n go to infinity of this term, 1 over 2 to the first plus negative 1 to the n over n, this one will be, okay, gonna go to 0 as n go to infinity, right? So we're gonna limit n go to infinity of negative 1 over n equal to 1. Okay, so it's gonna be limit n go to infinity of negative 1 to the n times 1 over n. And this one is your sequence bn. Okay, and you have limit n go to infinity of bn, n go to infinity of 1 over n becomes 0. Okay, and we use the theorem on the limit. We can conclude that this guy, you have limit equal to 0. I believe that this theorem is going to be on page 11. Okay, so let's go back very far. Okay, so it's going to be here. Okay, so you see that it's going to be number 4 when you have negative 1 to the n a n. It's going to be conversion to 0 when you have limit n go to infinity of a n equal to 0. So, okay, so we gonna go here. And it's gonna be, okay, 0. So we're gonna put 0 here. Okay, so this guy become 0. And so it's gonna be limit. So it's gonna be 1 over 2. Okay, so you have the limit equal to 1/2, and this guy is smaller than 1. Okay, so the series n equal to 0 to infinity of 1 over 2 to the n plus negative 1 to the n is absolutely conversion. Okay, so that will be the root test and the ratio test. Okay, I'm gonna continue with a little bit on the application of the ratio test for you, okay, which is gonna be on the next section, which is about the power series. I'm gonna skip page 37. Page 37 is gonna be about the conclusion for series test. The conclusion for series test, I will discuss this one with you during the recitation. So this one is gonna be, you're gonna have to feel during the recitation. It's gonna be about how would we know what test we're gonna use, and it's gonna be what is the strategy for testing the series. Okay. The power series will be, you see that it's gonna not look like the ordinary series. It's gonna be the function in terms of x. So you see you have variable x here, okay? And it's turned out to be coefficient C0, C1, C2. And when you plug in, okay, when you plug in x with real number, for example, you plug in x with 1/2, you can plug in x with 1, you can plug in x with 2, you can plug in x with negative 1, something like that. It's gonna turn out to give you the series, okay? So the power series is gonna be like a function in terms of series. And the thing that we're gonna have is gonna be, you have C0, C1, C2. They are called coefficient, Okay, it's like polynomial. However, this one turned out to be an infinite term. So this one is coefficient of power series. Okay, so it's gonna turn out to be C0, C1, C2, and C. And this one is gonna be power series about x equal to 0. Okay, so you see that it's gonna be x only. However, we be able to have power series about x equal to a. When you have x equal to a, the term for x gonna be changed to x minus a. Okay, so it's gonna be x minus a, x minus a squared, x minus a to the third. And we're gonna call a center. Okay, so we're gonna call a the center. Okay, so the power series turn out to be the function that when you plug in x, it's gonna give you series. Okay, it's gonna be series, and it's called power series, and it's gonna be depend on x for conversion or diversion. Okay, it's gonna be depend on x for conversion or diversion. For example, in example 30, so you see the question asks you for what value of x that we have this power series conversion. Okay, so for number one, it's going to be series n equal to 0 to infinity of n factorial x to the n. One thing when we dealing with power series, we're going to begin the term n equal to 0. Okay, so the term that we're going to be initiate is going to turn out to be n equal to 0 also. It's not going to be begin at n equal to 1 like we used to have. For this one, we gonna apply the ratio test. So this one, you see that you're gonna have your function in x. So it's gonna be unx. Okay, so un, and it's gonna be a function in x. So you have your unx given by n factorial times x to the n. Okay, and we're gonna use ratio test. Okay, so use the ratio test. So we compute un plus 1x. Okay, so un plus 1x over unx. Okay, so un plus 1 is mean that you're gonna replace x, you're gonna replace n with n plus 1. Okay, so you're gonna replace n with n plus 1. So for this one, it's gonna be n plus 1 factorial. Okay, you're gonna have n plus 1 factorial, and you're gonna have x to the n plus 1, and it's gonna turn out to be on the bottom, it's gonna be n factorial x to the n. Okay, and when we like to use the ratio test, you must put the absolute value. So you're gonna just put absolute value like this. Okay, and you would just simplify. So you can simplify n plus 1 factorial and n factorial. N plus 1 factorial, this one, okay, will be n plus 1 n time until 2 time until 1. Okay, n factorial is n time until 2 time until 1, and you can get rid of these two terms. Okay, and you have x to the n and x to the n plus 1. So this one, you're gonna have x. Okay, so this would be just n plus 1 that you have left. Okay, and you have x left, and it's gonna turn out to be inside absolute value. Okay, so this one will be this term, and you would just compute limit and go to infinity of absolute value of un plus 1x over unx. So it's going to be limit and go to infinity Okay, so it's going to be limit n go to infinity, and you're going to just put this number in. So it's going to be n plus 1x. And you see here n plus 1 turn out to be infinity. Okay, if x is real number, it's going to turn out to be infinity, except when you have x equal to 0. So let me separate two cases. When x equal to 0, okay, so when x equal to 0, this one turn out to be 0. Okay, so when x equal to 0, solid 0, it's going to be this term times 0, it equal to 0. So n disappear. Okay, so n disappear, so the limit turn out to be equal to 0. If x not equal to 0, it's going to become infinity times something not equal to 0. So it's going to be very large. So it's going to be infinity. So it's going to be 0 when you have x equal to 0. And it's going to turn out to be infinity when x not equal to 0. Okay. So you have this limit. And by using the ratio test, by using the ratio test, the thing that you're going to be able to conclude will be, so this one will imply conversion, this one will imply diversion. Okay, so this one will be conversion and this one will be diversion, because the limit equal to 0. Okay, so the limit equal to 0 is smaller than 1. Okay, 0 less than 1. So it's gonna be in the case that you have conversion. Okay, so this one is conversion and you have diversion for the second case. So we're gonna have the conclusion that the series n equal to 0 to infinity of n factorial x to the n turn out to be conversion if x equal to 0, and it is diversion if x not equal to 0. Okay, so that will be the conclusion. So you see, it's going to be the function in terms of series, and we like to determine whether our function is conversion or diversion, and it's going to become a power series. Or you may think about power series in terms of infinite polynomial. So it's going to be like you have, normally when you have polynomial, you're going to stop somewhere. Okay, so it's going to be look like this. However, if you have infinite tail of polynomial, okay, so this one may be called tail. So it's going to be infinite tail of polynomial. So you're going to have the thing that called power series. For the next one, you have different thing. So it's going to be x to the n over n factorial. So this one will be my unx. Okay, so that my unx. So let phi un plus 1x over unx. So this guy will be x to the n plus 1 over n plus 1 factorial. And you have x to the n over n factorial. And you're going to put absolute value like this. And then you get rid of, okay? So you get x, okay? And you're going to have n factorial like we used to have. So for this one, it's going to be n plus 1, n time until 2 until 1. And this one will be n time until 2 until 1. And you get rid of this number, like this. So the thing that you have left in this case would be, so you have 1x left and you have 1n plus 1 left. Okay. And you see that when you compute limit n go to infinity of un plus 1. I forgot absolute value. Let me put absolute value here. Still, you have absolute value. So it's going to be un plus 1 x over un x. So this guy will be equal to limit n go to infinity of absolute x over n plus 1. So you see that it's going to turn out to be x over something large. Okay, so it's going to be x over something large, and it's going to turn out to be always equal to 0. And this guy is smaller than 1. Okay, so this one, x turned out to be constant, x not vary, x is gonna be fixed x. Okay, so you don't think about x can be anything, x can be x only, and it's gonna turn out to be constant, and it's gonna be constant over large, so it's gonna become 0, and it's gonna be less than 1. So when you have the limit less than 1, so the conclusion for here is gonna be conversion. Okay, so the series n equal to 0 to infinity of x to the n over n factorial is conversion for any x in R. Okay, so it's going to be for any real number x. Okay, so that will be conversion for any x in R. The next one, okay, the next one will be you have the series n equal to 0 to infinity of x minus 2 to the n over 3. Okay, for this one, if you take a look, it's gonna be something raised to the n power. And this one, if you recall, let me highlight. So this one, I highlight yellow. Okay, so I highlight yellow. So this one will be series n equal to 0 to infinity of r to the n. Okay, so it's going to be of r to the n. And in this case, r will depend on x. So let me put it this way. It would be better to write rx to the n. Okay, so this one turned out to be geometric series. Okay, so this one turned out to be geometric series. And you know that this series n equal to 0 to infinity of x minus 2 over 3 to the n. So it's going to be conversion or diversion depending on r. So it's going to be conversion if x minus 2 over 3 put absolute value smaller than 1, and it's going to become diversion if you have absolute value x minus 2 over 3 greater than or equal to 1. So this one will be the term that you have here. Okay, so it's going to be conversion or diversion. And then you're gonna see that, okay, what can we conclude on this one? It's gonna be the thing that you can solve. Okay, so we're gonna solve this inequality a little bit. Absolute value of x minus 2 over 3 smaller than 1. Okay, so we like to know where our x. Okay, so where our x. So we're gonna solve this one, and you see that you just multiply everything by 3. So it's going to be absolute value of x minus 2 smaller than 3. So don't forget that the way to solve this one is mean you have the thing inside the absolute value. Okay, the thing inside the absolute value must be lie between 3 and negative 3. Okay, so this one is elementary algebra. And you have negative 3 plus 2 smaller than x smaller than 3 plus 2. So it's going to be negative 1 smaller than x smaller than 5. Okay, so after you solve this one, you're gonna get the interval x between negative 1 and 5. So you're gonna draw a real number line. Okay, so you're gonna draw a real number line and you would just put negative 1 and 5. Okay, and you have x line between these two guys, so it's gonna be this guy. Okay, so it's gonna be conversion. Okay, so this guy is gonna give you in the case that you have conversion. Okay, so you have conversion and you're gonna have diversion outside. So diversion. So when you have divergence, it means x is more than 5 or equal to 5 and x smaller than negative 1. Okay, so you are having the divergent case. And when x between negative 1 and 5, so you're gonna have the series turn out to be convergent. Let me put the red color here. Okay, so it's gonna be diversion outside and it's gonna be conversion in the middle. Okay, so that is gonna be the place where the series turn out to be conversion or diversion. Another thing is gonna be you have this series. This series can also be written in the form, okay, series n equal to 0 to infinity. And you see that this guy can be written as x minus 2 to the n over 3 to the n. And if you compare with the original series, so you see that you have x minus a to the n. And in this case, your a turned out to be equal to, okay, so your a turned out to be equal to 2. Okay, so a equal to 2. So this one gives you center. Okay, so this one gives you center. And I will explain why this guy is center. It's because 2 lies in the middle between negative 1 and 5. Okay, so the way to see this one, you can see this one is going to be x minus 2 less than 3. Okay, so if you take a look here, you have absolute value of x minus 2 less than 3. It means what? It means you're going to put 2 in the middle and you're going to walk 3 units. Okay, so you're going to walk 3 units out from to the left and you're going to walk 3 units to the right side like this. So when you walk 3 units, it's going to become 5. Okay, and when you walk 3 units to the other side, it's going to become negative 1. And that's why we call 2 center. Okay, it's center or it's in the middle of the conversion actually. Okay, so this one will be convergent or divergent. And you see that when we have center, normally we're going to have radius. Okay, so the thing that you can see is going to be, hey, can we call this guy radius? It's 3, you said. Okay, so you may ask me, hey, it's 3, and 3 is radius because if you consider it's kind of circle. Okay, so it called radius, and this thing will be called radius of conversion. Okay, so this thing is called the radius of conversion. You have a name for it. Okay, so it's radius of conversion equal to 3 in this picture. And you see that it's going to be center at equal to 2. So if you compare with this situation, you're going to have A, which is your center. Okay, so you have A, which is your center, and you're going to have the radius of conversion. So it means that inside this one turn out to be conversion, and outside is going to turn out to be diversion. And this interval, okay, so this interval will be called interval of conversion. Okay, so this interval is called interval of conversion, and it's going to be conversion inside this interval, and it's going to be diversion outside this interval. Okay, so you see the picture here. The picture here is going to be conversion, okay, and it's going to be diversion outside this interval. Okay, so it's going to be diversion outside this interval, and you have the thing that called interval of conversion. Okay, so interval of conversion. Another thing will be, hey, how about this guy? Do we have interval of conversion for the first two? Let's try to draw a picture. So for this one, you see that if you draw the picture, you're gonna have the center turn out to be at 0. Okay, so the center turn out to be at 0. Why did I say that? Because it's x to the n, x to the n, x equal to 0, center. Okay, so you have the center is at x equal to 0, and you see that it's only convert here. Okay, so you see that it's going to be conversion only at the center. Conversion only at the center, so it's too small. Okay, it's going to be just 1 point conversion, and it's going to be divergent for the rest. Okay, so it's going to be divergent for the rest. Okay, so here it's going to be the situation that it's turned out to be convert only 1 point at the center. Okay, convert only 1 point at the center, and it's going to turn out to be diversion for the rest of the point. Okay, so it's going to be convert only 1 point. So if it in this situation, the thing that you would say is going to be r equal to 0. Okay, so the radius equal to 0. Okay, we're going to have another n, which is this case. This guy turned out to be convergent for any real number, and the center turned out to be at x equal to 0 as well. So it's going to be 0 in the middle. And this guy, you have center. Okay, and for this one, it's very nice that you're gonna have it's turn out to be conversion all the time. Okay, so this one turned out to be conversion all the time. Okay, so this one is going to be another n that you have is conversion for every point. So in this case, the radius of conversion turn out to be infinity. So it's going to be like a convert at any value. So for this one, okay, this situation, the radius of conversion equal to 3. Okay, so it's going to be just 3 steps from the center on the left side and on the right side. Okay, so that's going to be this conclusion. Okay, so this one is a theorem, and you're gonna have the radius, and you're gonna have the center, and you're gonna have that the first case is called radius of conversion equal to 0. The second case, you have the radius of conversion equal to infinity. It means it converts at every point, and the last one is going to be the radius of conversion equal to 3. So it means 3 steps from the to the left and 3 steps from the right are gonna turn out to be conversion. Okay, so this one is gonna be just is for this lecture. Okay, so the thing that we used to determine turn out to be the what is called the ratio test. Okay, so that's why I teach you in the same clip. Okay, so that's all.